Hello everyone. I welcome you all for today's webinar. We are excited to have you explore about Rotordynamics. So we'll begin the webinar session shortly. Feel free to use the question box for the questions and chat for the comments. So now I request Muthu Kumar sir to begin this.
Hello all, good morning, good afternoon, good evening, depending on wherever you're joining us from. I extend a very warm welcome to each one of you. It's truly an honor to host such a diverse and international audience. And we are grateful that you have taken time to be with us today. So this webinar we consider is a wonderful opportunity for all of us to connect, share ideas, gain valuable insights, and it is your presence and participation that makes it all the more meaningful. To ensure a smooth experience, all participant microphones will remain muted during the presentation except the speaker. And at the end of the webinar, you will have a dedicated Q&A session, which you can unmute yourself and ask questions, or you can email your queries in the chat window or use the chat window so that we'll actually get back to you. Today's session will focus on the topic, maybe next slide. Today's session will focus on the topic in our FEA learning series, Rotordynamics FEA, using Ansys mechanical software, along with a live demo on how to do an unbalanced response analysis. Before getting into the webinar, I would like to share a very brief introduction about APA and then talk about a presenter. So APA is a 25-year-old 500 people organization headquartered in India, serving clients across USA, Canada, Germany, Netherlands, and Australia. We are ISO 9001 certified for the quality management, ISO 27001 and TISAC certified for information security related processes. These certifications helps us in delivering a high quality services, ensuring a very strict adherence to global data security standards, providing the confidence and kind of a peace of mind to our customers. Our services can be categorized into 4 divisions: sourcing, engineering, compliance, and technology. Very quick on sourcing team, which helps our clients to identify a right supplier for their manufacturing needs. We conduct quality audits during various stages of manufacturing, do a pre-dispatch inspection, optimize the logistic costs, and through a consolidation of our warehouse, and ship the products to our client's doorstep. We'll talk about engineering in a bit more detail in the next slide. Compliance team offers software products and services to clients, helping them to comply various product chemical compliance requirements across the globe, such as conflict minerals, IMDS, REACH, ROHS, PROM 65, including the latest SKIP and PFAS. Our technology team is into providing software products and services to improve enterprise productivity through a smart and custom-built IT products and solutions. Now, I'd like to take you through our engineering services and skill sets. Next slide. So, engineering division is a 80-member strong team comprising of mechanical engineers and electrical engineers. And our services can be divided into product engineering, manufacturing engineering, plant engineering, digital modeling, and embedded engineering. For the interest of time and today's audience, we will particularly go over product engineering and manufacturing engineering services a little bit in detail. With our knowledge in design manufacturing, we create parametric 3D models, prepare manufacturing drawings, measurement details, machining details, GD&T information, all that as per ASME or DIN or ISO standards. Oftentimes, we call ECOs or engineering change orders, basically design updates or design completion, where the client provides the concepts for us to finish the design. If the requirements demand, we can also have the capability to design from the concept level. We have a reverse engineering lab. We're doing a scanning and probing of the physical components, get the cloud point data, and use a conventional 3D software to create a parametric model and 2D prints. We validate the design by performing FEA simulations, predicting strength, stiffness, fatigue, vibration, and impact resistance. We have the capability to do a thermal and flow simulations also. We also support on standardization of design variations and weight optimization using topology, size, and shape. and material conversion projects such as iron to aluminum, sheet metal to injection plastic molded parts, kind of a project we undertake. The manufacturing engineering space, we based on the customer requirements, we work on 5M resources optimization, which is nothing but man, machine, methods, materials, and measurements. We provide solutions to improve the efficiency of the solutions, often supported by doing FMEA, failure mode effective analysis. Part of this service goes into layout optimization and balancing the throughput time. And we do design, redesign of the fixtures, toolings, and gauging systems, and also CNC programming to improve the setup time, tool life, operating time, and towards minimizing the downtime. We can also take care of the PPAP documentation. So we provide engineering services in automotive, oil and gas, special purpose machine, medical equipment, and plant engineering fields. We work with companies in different domains and also varying sizes from a single person to all the way to a very large organization. So that's all about. I want to talk about the engineering team skills and capabilities. Now we'll move on to today's speaker. Next slide, please. So Jason Sampson is a senior FEA engineer at FEA. He's a mechanical engineering graduate, and he also done his master's in industrial engineering. Overall, 6+ years of experience post the masters, and he's extremely strong in performing linear, non-linear analysis in strength, durability, and vibrational performances areas, which is missing here. And also, he is a sheet metal design expert for automotive and heavy industries applications. Over to you, Jason. Do you want to take us through this today's webinar?
Yes, Muthu. Thanks for your introduction, and good evening to every attendees. And thank you all for taking your time and joining this today's session on Rotordynamics FEA using Ansys Mechanical webinar. And in this webinar, I'll walk you through the fundamentals of Rotordynamics, how to interpret critical speed, whirling, and I will spend some time on Campbell diagram, how to understand it. And finally, we'll look at unbalanced response simulation demo. So at the end of demo, we will have a Q&A session. So as you watch this webinar, if you have any questions, you post it in the chat window, and at the end of the webinar, we will try to address them. So first of all, let's understand what rotordynamics is. So rotordynamics is the discipline that deals with predicting and controlling vibration, critical speed, and stability of rotating machinery. And this is extremely important because rotating equipments like turbines, compressors, pumps, and motors, they typically operate at very high speeds, and even small imbalance can cause large vibration issues. And one of the most common cause of this vibration in rotating machines is unbalanced rotating force. And we will look what is unbalanced rotating force in the next slide. And so this unbalanced response analysis can be used to predict the critical speed, mode shape, and so on, stuff like that, and which can be helpful in accelerating the product development cycle. And I have listed a few causes. Excessive vibration. So higher noise levels, reduced bearing life, unsafe working condition, and it can lead to overall reduction in the machine life. So the rotordynamics study helps us ensure reliability and safety during the overall machine operation. And so, like I said in my previous slide, the most common cause of excessive vibration is due to rotating unbalanced forces. Now, let's look at what is the meaning of unbalanced rotating force. So consider a disc on the rigid support like this, and it's spinning with a particular angular velocity. And consider a tiny little mass on the disk, and this mass is creating an unbalanced force, and this will cause the vibration, the lateral vibration of the rotor. And so our goal will be to control this vibration through rotordynamics study, so as to ensure reliable and safety during the machine's operation. And the unbalanced rotating force can be given by the equation given here: mass times eccentricity times the angular speed, the rotation velocity squared. And let's come to what causes the unbalance in the rotating system. It could be whether the manufacturing tolerances, or the variation in the material density, or the accumulation of dirt or deposit over the period of time. It could be a wear or erosion, corrosion, and unbalance could be due to thermal distortion or machining inaccuracies. So let's see what is unbalance response analysis. Unbalance response analysis is one of the most important simulation in rotordynamics. It predicts, like I said earlier, how a rotor will vibrate when it's subjected to a mass unbalance, or like in the previous slide we saw unbalanced rotating force. What if the unbalanced rotating force is acting on the rotating equipment? So we will study such aspect through unbalanced response analysis. And some of the purpose I have listed here is for the unbalanced response analysis study is to determine the reaction force acting on the bearing, and to identify critical speeds, meaning the point where the rotor vibration is going to peak. And we also can evaluate how bearing stiffness, damping, and mode shape is going to influence the vibration levels. So these are some of the purpose of unbalanced response study. And in short, the simulation helps us how the rotor behaves in a wide range of operating speeds, and so that we can ensure safety and stable operation. So I will introduce a few concepts: critical speed, what is a critical speed, and what is whirling. And critical speed is a rotational speed at which resonance occurs, right? So what does it mean? It means when the rotor's vibration amplitude spikes due to a matching natural frequency, then we say the rotor is at its critical speed. And this is a dangerous zone, and we should avoid it. And we cannot completely eliminate it, but we can design machine in a way that it accelerates through this critical speed quick enough. And our focus will be that the operating frequency are away from these critical speed zones. And let's talk about whirling or whirl motion. So whirl motion is the lateral vibration of the shaft, where the center line of the shaft traces a circular or elliptical path while it's rotating, while it's spinning at a particular speed or frequency. And there are two types to it. One is forward whirling, and the other is backward whirling. So if the whirl direction is same as the direction of the shaft, then we call it as a forward whirling. if the whirling direction is opposite to that of the shaft rotation, then we'll call it backward whirling. And so these both forward and backward whirling modes play key roles in rotor stability. So understanding it will be crucial in our rotordynamics study. And so this brings us to the one of the most powerful tools in rotordynamics, the Campbell diagram. I will show you how to create one in the demo session. And a Campbell diagram plots natural frequency against rotational velocity. So we'll have a rotational velocity in the horizontal axis, and we will have the natural frequency in the vertical axis. And so these the lines we could see, right? These are the natural frequency lines, and you could observe that the curve is positive. The slope of the curve is positive, meaning that it's forward whirling. The slope is negative, meaning it's in backward whirling. The mode shapes are in backward whirling. And also you could see a dark line. If you could follow my cursor, the bold line is called the excitation line. And usually for unbalanced study, the ratio will be excitation ratio will be 1. And so wherever the natural frequency crosses the excitation line, it is indicated by a little red triangle. So these triangles are the critical speed, and from this information, the designers can choose, can see if their rotor is going to be operating if there are any critical speed at their operating ranges, which could be really helpful. So we will jump on to Ansys to see the demo session. And so our goal here will be we'll find the natural frequency mode shapes between 0 and 100,000 RPM. We will create Campbell diagram, and we will plot the peak vibration response in terms of displacement. We will also plot orbit plot. I will jump over to Ansys. So, what we will do is we will first do a model analysis to study the natural frequency, and we will extract the Campbell diagram. So from the Campbell diagram, we can understand the critical speed, and we'll take a note of those critical speeds, and then we'll use that information in the subsequent harmonic analysis we are going to do. In the harmonic analysis, we will apply unbalanced mass to the rotor, and we will find the response to that unbalance in terms of displacement, and we will plot the orbit plot. That's the goal of this demo. And I have a fully solved simulation here, and I will for the interest of time, what I'll do is I will show you how to do the setup hands-on, and I will jump over to the completed simulation to show you the results. So this is the completed one. Here I have the partially completed analysis. So we have the rotor splitted into about the vertical and horizontal axis, and we have I will show you. So we have splitted the rotor into 4 parts, and also there is a shared topology option to get the coincident node on these two, on the common face of the two bodies. So this has been done so as to get a common node at the spin axis, right? So we will get a spin axis if we could reset the exploded view and turn on the wireframe mode. In the name selection, I will turn off the edge connection. So you could see the spin axis, right? So to get the spin axis, I have followed that workflow. So I will turn off the wireframe mode. So we will use the default structural steel material to the rotor. We'll apply it. And I want to show you the boundary condition once. I have it on my slide. Let me show it. So what we'll do is we will apply a rotational velocity to the rotor, and we'll model a point mass at this location. You could see this label A, right? At that particular location, we will create a point mass, and at location C and D, we will create a Combi 214 Ansys bearing element, and we will constrain the bearing element in such a way that so this is the x-axis is along the spin axis. So we will constrain the translation in its direction, also rotation about the its direction. So that's what the C and D boundary condition says. I will also show you the input parameters that we'll use for this analysis. So we have the input rotational speed, we have the bearing stiffness. So these are orthotropic bearing stiffness values. And we have the mass and inertia properties that we will use for the point mass, which is for this location, label A location. And in the harmonic response analysis, we will apply this unbalanced mass 1 gram mm. So again, I'll jump onto the Ansys session. So I will go ahead. I'll right click on the geometry tab, geometry branch, and I will insert the point mass. I'll quickly peek into the point mass properties on 0.4103. I will. So I have created a prior to this demo session. I have created the name selection. So I will use this name selection for point mass. I'll select the scoping method as name selection. I will choose point mass, and I'll apply the weights. 1.4103. $2,013,600. So with that, I have defined a point mass. You could see right here. It's just a visual representation that we have created a point mass. And I will. So I have gone ahead and created name selection at the location where the bearing is going to come. So this is for the location where the bearing 1 will come, and at this location bearing 2 will come. And so since this is, I will talk about the connections here. Since this part is made of 4 bodies, I have used contact to connect all the separate bodies so that the rotor behaves as one. Now I'll use Rotordynamics tool Act app. So to create the connections, the bearing connections using name selection. So to do that, what we should do is we can pre-select the bearings and click on the bearing dropdown, and you could select create bearings from name selection. And two things happen. One is that we have two bearing elements created, and also if you have noticed, there is two rigid spider or remote points have been created. See, right, at the two bearing location. And what I'll do is now I'll define the bearings. I will control select bearing 1 and bearing 2, and since I am going to assign the same properties for both the bearings, I will control select both of them, and I will enter the properties. So I will leave the connection type to body to ground. Then I will choose a rotation plane as YZ, since the spin axis is oriented at its axis, our rotation plane will be YZ. So YZ. And we should input the autotropic bearing stiffness values. So I'll just peek into the PPT. Three 5030 Newton mm, 35030 Newton per mm. 8756. So with that, we have defined our bearing stiffness values. So these are 2D bearing element, and the the annular disk you are seeing here is just a representation that yeah, bearing element has been created. If you want, you can turn it off. Okay, it's not real. And so also I will create a remote point at this point of time. So at the unbalanced, so like I mentioned previously, we are going to, after completing the model analysis, we are going to go with a harmonic analysis. In that harmonic analysis, we will apply a rotating unbalanced force. And to do that, I need to create a remote point. I need a remote point, so I will do that now. I will set the scoping method to name selection. I will choose this unbalanced phase, and I'll rename this. So we have done the connections, we have done the machine. So I have used a 5 mm element size to all the bodies, and I have applied phase meshing. And so coming again to the named selection, I will show you one thing. So so the red line you could see is the axis of rotation, or the spin axis. I have gone ahead and extracted nodes from the spin axis using the worksheet. So this will be useful in while we are generating the orbit plot. Okay, so now what I'll do is I will control select the bearing, and I will create the bearing constraints. So now we have defined the bearing constraints. Let me orient it. Like I said during the boundary condition discussion, we have constrained the translation about the x-axis and rotation about the x-axis. That's what this the remote displacement constraint means. You could see the x component, the translation in x component is constraint, 0 meaning it's constrained, and as well as for rotation about x is 0 degrees. The remaining degrees of freedom is set to free. And I will walk you through the analysis setting. So I will request 12 modes, and I will use damped solver, and I will turn on the Coriolis effect to account for the gyroscopic effect due to spinning. That's how we get the elliptical plot while we are plotting the orbit plot. And I will set the Campbell diagram to on so that we can insert Campbell diagram while we post process the results. And I'll set the number of points as 3, and this is corresponding to the number of rotational speed we have. I'll right click insert. So while we are talking about the points, I'll just create the boundary condition rotation velocity. So you could see 3 points right here because we have set under that analysis setting the number of points to be 3. If you miss to update it, you could not see the rotational value. By default, it's going to show only one rotational velocity. That's one thing to note. I'll again go back to the analysis setting, and I will leave the rest of the settings as it is. I will now specify the rotational speeds. So I will specify it as components. I will click this little arrow and choose tabular, and I will enter our rotational speeds, 50,000 RPM and 100,000 RPM. Only to the power 5, yes. And with that, our model analysis setup is complete, and we can hit solve button, but I will show you the completed analysis. So we can right click insert, come to Campbell diagram, and if you choose that option, you can insert the Campbell diagram. Like I said before the demo session, we have Campbell diagram plotted against natural frequency. Sorry. So we have rotational velocity at the horizontal axis. We have natural frequency at vertical axis, and we have a dark line, which is the excitation line. And this excitation ratio is set to 1, and this is what we typically follow for unbalanced response analysis. And the location where the natural frequency is equal to the excitation line, or the matches with the rotational frequency, we have a resonance condition, which is called the critical speed, and these are marked by the little red triangles. And you could see we could also get information about each mode, whether it is a backward whirl or if it's a forward whirl. And you can control click on any of these points to get what's the frequency. You can probe in that way. You'll control click, and you'll hold the control button and click on any point. You could read the result that way, and other way is to read the results from the table. and I have inserted the mode shapes prior for the benefit of time. So you could do that by coming to here, selecting whatever you could select all, Control A, and right click, create mode shape results. So now I'll go on back to our modal analysis. While I'm here, what I'll do is I will go to environment. I'll choose harmonic response under analysis setting. And under analysis setting, I will define the range, and our rotational velocity range is 100,000 RPM, which is close to 1,600 hertz. And since this is a demo, I will specify the range as 2,000 hertz, and I will specify the solution interval as 40. I will turn on the user-defined frequencies, and so I have copied the table from the Campbell diagram previously, the one I showed earlier, and this is the table we saw below the Campbell diagram, and it has speed in RPM. So while we are doing unbalanced response analysis in harmonic analysis environment, and while we are performing this harmonic response analysis as a full method, we need to specify user-defined frequencies. So what I have done is I have picked 2 points above and below each critical speed. And in addition to the solution interval that I have specified in the analysis setting, I will use all these values so that I will not miss any critical speed while while we query the unbalanced displacement chart, the results. So what I'll do is I will copy the user defined frequencies. I will go to the Ansys mechanical. It's showing yellow since we haven't specified any user defined frequency. So I'll paste it here. So in addition to the 40 solution intervals, the analysis will also look for these specified critical speeds. And the solution method should be full. And I will turn on the Coriolis effect on. And I will define the constant structural damping as a direct input as 0.1%, meaning 0.01, 1 e to the power minus 2. And also we need to apply the bearing constraints to the model. So what I'll do is I will control select the bearing constraint that we have already created for the model analysis, and I'll drop it onto the harmonic response environment. And so the only one thing that that is pending is that we have to create an unbalanced force. I will do that by insert rotating force. I will choose this phase. I will define the coordinates. Okay, we haven't created a coordinate. Maybe I can do it now. Insert coordinate system defined by name selection. So I'll use the unbalanced phase. which is scoped to the all 4 phases. And coming back to the rotating force window, we could specify the coordinate system, and I will specify the unbalanced mass as 0.001 kilograms or 1 gram, and the eccentricity as 1 mm. And I will choose the hit point selection as remote point, and I'll use the previously selected unbalanced remote point location. And if you have successfully created it, created the hit point selection, you would see the hit point node ID here, or else you will see red or orange kind of light in this selection, in this tab, in this field actually. So with that, the setup for an harmonic response analysis is complete. And if we can run it. And for the interest of time, I have plotted the results in the presentation. Also, I will tell you how to read, get the results. Right-click, insert the solution branch. You will see the frequency response, and you will insert deformation, and you will get something like this. And we'll set the orientation as Y. You can choose it as either as Y or as Z. And we will select a critical the interest, whatever frequency we are interested. We can choose it under the frequency from the frequency response table. Here you could find the frequency response chart, and you can insert the frequency to get the directional deformation for the corresponding frequency response. Maybe let me. So if you want the displacement response for this particular frequency, what you will do is you will right-click, insert deformation, and you choose directional deformation, and you would get something like this. And you will specify the orientation, the frequency, and the frequency which we have just now saw. I have probed, right? So that particular frequency and the phase angle, you could find it from here, or you could hold the control and click on your left mouse button to get the amplitude and phase angle. And the frequency value, you could get it from here. So what you need is two things. One is frequency, and the other is a phase angle. And you can then right-click and retrieve the results to get the results. And so this is the frequency unbalanced response chart in terms of displacement. And these peaks are the critical speed. And for this demo, I have only we have only chose 40 to 50 points. Yeah, 50 points. So if we choose, if you choose the interval in a way that we could select more points along the frequency chart, then we can get a more smoother curve. That's one thing I want to tell you. And I've also gone ahead and created an orbit plot. So we can, in a similar way, we can right-click on the solution branch and insert an orbit plot, this option, and we will specify the frequency number. This number we can get it from the frequency response chart. This. And we can get the particular frequency for that particular mode. And we should specify what is the spin axis. We should not specify it Y or Z, unlike we have done it in the directional deformation option. And I have set the scale factor to 2 just for visualization purpose. Give me a second, I'm checking one thing. Yeah, so the frequency number is corresponds to the number at the frequency response chart number 9, right? 211.7. Could see that here. So I will now jump on to Ansys. Sorry, the presentation slide. Give me a second. Okay. So I have the results for this analysis here. We have the Campbell diagram here, which we saw earlier. So this is the frequency response chart, and we have plotted displacement against the natural frequency in this plot. And finally, we have the unbalanced response chart. So this concludes our the end of demo session. So if you have any questions, please feel free to drop it in the chat box, and we'll try to address them. So I can see some questions here, and will answer the one that is that will be useful for everyone. So how do you find the bearing stiffness? So the best solution would be to contact the bearing manufacturer. They might have the stiffness values with them, and that's one way you can get the bearing stiffness value. And there is also an Ansys Act extension app, like the Rotordynamics tool app, that we have used to create the constraint and the bearing constraint a while ago. So similar to that, Ansys Act app is there, developed by SKF Bearing. If you are using any of the SKF Bearing, you can use that bearing designation and get the stiffness value out of that app. And another question is the excitation ratio always 1? So to answer your question, it's not. No, it's not always 1. Sometimes if you're analyzing a rotor with impeller on it, and due to aerodynamic excitation, so for each rotation, due to the number of due to the number of vanes on the impeller, there will be equal number of excitation. Say if you have 12 vanes on the impeller, and for a single spin, there will be 12 excitation. So that time you should define if the excitation is 12, since the excitation corresponds to the number of plates on the impeller. So can you show how to install Rotordynamics tool app? So you can try the Ansys Act store to get the Rotordynamics tool app. It's in there, and you can find a wealth of resource online. if you couldn't, I can also reach out to you separately to show you how to install that Rotordynamics tool app. So with that, I'll conclude this Q&A session. I will answer the rest of the questions. I will reach out to individual attendees and answer those questions. Thanks everyone for your patience, and thanks for your time in attending this webinar. Over to you, Muthu.
Okay, thank you, Jason. It was really an informative session. Yeah, Muthu sir, you want to speak something?
Yeah, so just on behalf of all of us in APA, so definitely a heartfelt thank you for joining today's webinar. Definitely we appreciate your time and interest, and I hope that the session provided some insights to you. As we conclude, you will receive a short survey form. Kindly request you to take a moment to share your feedback, suggestions, any questions. As Jason said, that we will definitely come back to you, reply to your questions, and we will help you to learn about the Rotordynamics FEA simulations. Thank you all. Looking forward to meet you in yet another FEA learning series in the coming months' time. Thank you so much.
Yeah, thank you everyone for joining our webinar. We are glad you took this time to learn about Rotordynamics with us. So we hope you found this session insightful and gained some valuable ideas. We would love to hear your thoughts. So please take 2 minutes to provide us the feedback through the survey. So the survey form will show up once the webinar is ended. Thank you one and all.